Hi, my name is Eric Noor.
My name is Baptiste Lemaire.
And my name is Andrew Lim. And today we'll be presenting our work on Proteus, a self-designing range filter that navigates design trade-offs to meet practical constraints. Range queries are fundamental database operations that retrieve all keys that intersect with a given interval. Applications that need range queries and handle big data include social media platforms that aggregate user events over space and time, as well as pattern discovery and anomaly detection in time series data. Executing such range queries on large datasets is difficult, as they typically require expensive accesses to slow storage, and these costs are incurred to no benefit if the query turns out to be empty. Therefore, our goal is to create a memory resident filter for empty range queries that can help to avoid unnecessary overheads. Filtering range queries is a difficult problem. Bloom filters or other approximate membership query structures are infeasible for range filtering, as querying every member in the range results in an overall false positive rate or FPR that increases proportionally with range size. It has also been theoretically determined that an impractical amount of space is required for a range filter to support large ranges and have strong worst-case FPR guarantees. As such, state-of-the-art range filters typically forego general FPR guarantees in order to achieve a usable memory footprint. Current range filter designs encode key membership using two fundamental design elements: probabilistic Bloom filters and deterministic search trees. Rosetta and Surf are state-of-the-art range filters that use probabilistic and deterministic design elements respectively. These filters have fixed designs that are suited for different types of workloads. To better understand the behavior of these range filter designs, we identify two fundamental range query workload features, which we shall explain subsequently. We map the performance of Rosetta and Surf onto this workload space, and our performance metric is the filter's false positive rate. More intense colors represent better performance or a lower false positive rate. We see that each filter dominates separate regions of the workload space and struggles to perform well outside their intended use case. There is also a large region of the workload space, the top right-hand corner, that remains intractable for both filters. Our work Proteus flexibly unifies probabilistic and deterministic range filter designs, enabling it to outperform both Rosetta and Surf in their respective use cases. On workloads optimal for Rosetta, Proteus adopts a more Bloom filter-based design, while on workloads optimal for Surf, Proteus uses mostly a trie-based design. Proteus is also able to combine both probabilistic and deterministic design elements in a complementary fashion to perform well on the workloads that are intractable for Surf and Rosetta. To efficiently navigate its design space, Proteus uses an automated analytical model that takes the key set and a representative set of sample queries as input. Relevant features are then extracted, namely the distribution of range sizes, the distances between the queries and the closest key, as well as the number of unique prefixes in the key set of any given length. The range size and key query distance are the two fundamental workload features previously mentioned that define our workload space. This information is then plugged into the model along with a user-specified memory budget, and the output is the design parameters for a Proteus instance that minimizes the overall false positive rate.
Therefore, the core intuition behind Proteus is that filters with variable designs are performant and viable. We summarize the 4 key steps to build Proteus. So first, the cornerstone is our capability to leverage the context. We extract workload features to be performant. Then we can build a filter with flexible designs based off of workload features, the design parameters being chosen to optimize performance. On top of this flexible design, we build an automated analytical model to choose the right parameters and make a filter easy to use. Therefore, users with virtually no knowledge in data structures can efficiently handle a filter. And finally, to make automation practical, you need a lightweight functioning mechanism, which we achieved using minimal workload sampling to alleviate construction overheads. We use a variety of criteria to evaluate the performance of a filter compared with state-of-the-art filters. First, the most important evaluation metric is the end-to-end latency of real-world storage engines, such as RocksDB, when combined with a filter. Then we test the reliance of a model on workload features by exposing a filter to shifting or changing workloads. Finally, we assess our filter performance on real-world string workloads. Regarding the end-to-end performance, we observed that Proteus speeds up range queries when integrated into RocksDB, an open source storage engine. The end-to-end performance is determined by measuring the end-to-end latency for different memory budgets or bits per keys allocated to the filters. We also report the false positive rate as a metric of interest for Proteus, Rosetta, and Surf. We report here the instance of a uniformly distributed integer key dataset combined with a uniformly distributed range query workload. First of all, we confirm the strong correlation between low false positive rate and end-to-end latency. And second of all, we confirm that Proteus outperforms state-of-the-art range filters, in particular for tight memory budgets, where we achieved up to 3.9x lower latency compared with Surf and Rosetta. Then, because our filter is adaptive, we measure its robustness inside RocksDB when the workload itself is shifting. We are testing the robustness by exposing the filters to two extreme workloads. We start with a correlated query workload, which is challenging for trie-based designs, and we gradually shift to one with large uniform range queries, which is challenging for Bloom filter-based designs. We interleave queries from both distributions with a changing ratio over time. Here again, the cumulative latency is our main performance metric, but we also report the average false positive rate as the workload changes. Overall, we see that Proteus can outperform both Surf and Rosetta because of the performance advantage, but also because the sampling happens continuously and therefore even filters built on cold data are kept up to date. Finally, we look at the performance of a filter when exposed to string keys and queries. Proteus supports strings and the details are in the paper. So we built a workload based on a real-world dataset, the collection of .org internet domains. In the .org dataset, we used randomly selected URLs as keys and the rest as left bound of range queries, the right bound being synthetically generated with a uniformly distributed range size. We reported the latency and false positive rate for different memory budgets in RocksDB and compared Proteus with Surf, Rosetta not being competitive on this workload. Here, our filter consistently outperformed Surf with up to 5.3x lower latency. We can see that the difference in false positive rate was magnified in the end-to-end latency. This string experiment particularly highlights the advantage of Proteus of having no memory budget requirements, unlike Surf, which could not reach memory budgets lower than 16 bits per keys.
Now that we know Proteus is pretty great, let's dive deeper into its design, starting with the trade-off of its fundamental components. Both probabilistic and deterministic designs use prefixes of the key set to represent regions of the key space containing at least one key. Here we represent the key space encoded by a Bloom filter using 1, 2, or 3-bit prefixes, respectively. The prefix of the key set are shown in blue. The critical choice then is which prefix length to use, as a given prefix length may be too short or too long, depending on the use case. In this example, the longest common prefix between the key and the keys and the range query has a length of 3. Therefore, any filter with a prefix length of 3 or less will contain some prefix of the range query, resulting in a guaranteed false positive. Outlining the prefixes of our query here in red, we can clearly see this overlap. However, if we use a prefix length of 4, this is no longer the case, and the query will return negative unless one of the individual queries returns a false positive. This also illustrates how longer prefixes will result in a false positive rate that is more sensitive to range size, as more prefix queries will be required to cover any given range. If we instead use a search tree, we need only search for a leaf node containing a prefix of the key set. False positives can still result from shared prefixes if the tree is not deep enough, but the probability of a false positive is no longer dependent on the size of the range. The downside here is that encoding a tree of a given depth has a strict memory requirement, with deep trees often being too expensive to be feasible. In contrast, a Bloom filter can use any prefix encoding without a minimum memory requirement. With a better understanding of its components, we can now dive into the model at the heart of Proteus, which we will illustrate using the following example of using the following string keys. Our example instance of Proteus uses a tri-depth of 2 and a Bloom filter encoding prefixes of length 4. Empty queries fall into one of three different cases, determined by the length of the longest common prefix between the query and key set, or the LCP. The first occurs when the LCP is shorter than the try depth. For example, the query bundle to darts only shares the prefix B with the key set, so no leaf node in the try will overlap with the query, resulting in a guaranteed negative. The second case happens when the LCP is longer than the try, but shorter than the prefixes encoded in the Bloom filter. In our example, the LCP of the query shale to shanty is SHA, which does overlap with the leaf node of the try. Therefore, all four character prefixes of the query overlapping with the leaf node are then queried in the Bloom filter. In this case, SHAL, SHAM, and SHAN. The probability of a false positive is then dependent on both the false positive rate of the Bloom filter and the number of individual prefix queries, represented here by the terms P and M, respectively. Lastly, if the LCP of the query and the key set is greater than the prefix length of the Bloom filter, then there is guaranteed to be a prefix of the query present in the Bloom filter. For example, the query barrier to barrow overlaps with the prefix BARR encoded in the Bloom filter, and will therefore always result in a positive. Now let's take a look at the model in action. To do so, we will be comparing the configuration of Proteus and its false positive rate against Surf and Rosetta across different in-memory benchmarks. Our first workload contains small range queries that fall close to the keys, resulting in long common prefixes. This is favorable to Bloom filter designs as the effect of the range is minimal, while Surf performs fairly poorly as it has insufficient memory to distinguish keys from the correlated queries. We also see that Proteus is able to attain better performance than Rosetta on smaller memory budgets by compensating with shorter prefix lengths to reduce the number of Bloom filter queries. Moving laterally in the workload feature space, we maintain the same key query correlation while increasing the key query range size, while increasing the query range size. This increase results in a much larger penalty for Bloom filters with long prefixes, as seen in Rosetta's FPR, which never drops below about 0.5, even with a memory budget of 18 bits per key. Proteus, on the other hand, is able to balance the penalty for large ranges by using short prefix lengths. Without even introducing the try, Proteus is already able to cover more use cases simply by choosing an optimal prefix length for its Bloom filter. On the other end of the spectrum, we have uniformly distributed queries with large ranges. The large ranges, again, heavily penalize Bloom filters with long prefixes. But since the queries are uniformly distributed, most common prefixes will be shorter than the try, allowing it to be much more effective. As such, Proteus dedicates the majority of its memory to the try and performs similarly to Surf, but though its more flexible construction allows it to use smaller memory budgets. Now moving vertically in our workload space, we maintain large range sizes, but now use a mixture of uniformly distributed keys or queries and key correlated queries. In this setting, Surf can only filter the uniformly distributed queries, while Proteus is able to combine the try and Bloom filter in a complementary fashion to maintain a low false positive rate. Proteus takes a modest hit to performance at the lower memory budgets, but still far outperforms the competition. Through this flexibility of design, Proteus is able to achieve high performance over a much larger area of the workload space, even than Surf and Rosetta combined. Happy as we are with these results, there is still room for improvement. Seeing as our model only optimizes the false positive rate of the filter, there is potential to implement higher order policies that also account for query latency, enabling Proteus to handle applications that require more complex resource management. Moreover, while Proteus is able to address a much larger portion of the workload space than previous range filters, it still struggles in the upper right corner of our heat map, corresponding to large queries that are also key correlated. Both our model and our experiments suggest that this may be a hard limit on prefix-based filters, so we're excited to see what designs people come up with next. Thank you all for your time. And let me stop the recording. Come on, there we go.